allows them to observe the universe, but it's not about the telescope, even though you might nerd out about the telescope, right? It's about the stars. And I think the same thing is true about computers and computer science. Now, in this analogy, I am definitely like an amateur astronomer, and I don't know that much about how the telescope works, but I know bits and pieces, and so that's what I'm going to be sharing with you today. Is some of that like computational reality that permeates our world. I just wanted to share this quickly. So there's going to be some like resources that I talk about. There's going to be some code examples. I'm going to show this URL also at the end of the talk. But if you want to follow up and see those, you can go to this link. I also just wanted to show a few images of my own work. And in my own practice, I do immersive installation work, all using processing. And these things that I'm talking about computation allowing you to pull back the curtain on the universe and see the magic behind the curtain. This is something that I try to evoke in my own work. So I'm really interested in creating these kind of wonder-filled spaces with interactive digital interfaces. This is an installation I did for an apartment building that has this kind of pseudo-biological simulation running on it. And these organisms live and die on the side of this apartment building. And they kind of have this tension between order and chaos. Here's kind of a more chaotic state. So these are ideas that I'm kind of drawing from the sciences as an amateur, and then taking them to my art practice. And I think like learning this vocabulary about chaos theory is an important, it could be important for you too to think about as you're doodling and processing. Oh, this is another piece that I did. This is a projection mapped shoe retail thing, again using processing. Yeah. So to talk about chaos, first we have to talk about determinism. Determinism is this idea that the state of the universe now is completely determined by the previous state. So this is a way of looking at the universe that's kind of like looking at a clock. It's a clockwork analogy, where if you know all the mechanisms of the universe, you know all the laws of physics, and you know the position of every single particle, and you press play, you can kind of generate the next step of the simulation, right? And this is an idea that makes me feel kind of uncomfortable. It might make you feel kind of uncomfortable. I think we tend to have this natural tendency to argue against this because there's this cognitive dissonance between causal determinism and free will. If every brain state is determined by the previous brain state, then there's no room for me to exert my will, right? And I think that chaos theory is it's one way to kind of resolve that cognitive dissonance. It's maybe not the only way. It's maybe, you might not believe me that when you see what I believe, but I think it is just one interesting argument that kind of like resolves this conflict between determinism and free will. And the way that I'm going to approach this is to talk about predictability. I think we often conflate determinism with predictability. So we think that if we live in this, strict causal universe where one state determines the next, then everything is predictable. And that's what scares me. I don't want to be this like entirely predictable machine, right? I want to be a human. The thing is that determinism and predictability are not the same thing. That's a false assumption to conflate those two things. And this is what we're going to see when we create a chaotic system. You can have something that is deterministic and yet also unpredictable. So again, we're starting super big picture, and now in a bit we're going to like go super narrow and focused, but maybe keep this idea in the back of your mind because we're going to see how this actually works. We're going to build a deterministic yet unpredictable system. And we're going to do this in the context of dynamic systems. So dynamic systems are the mathematical study of systems that essentially change over time. And I think it's kind of fun to engage with a little bit of the jargon here. It's not super important, but again, it helps to have the vocabulary when you're thinking about your own work. So we're going to talk about different types of dynamic systems leading up to a chaotic system. The first type of dynamic system is something like this, where we have a valley, and we place a ball on the side, and then what happens to the ball? It rolls to the center of the valley and eventually stays there. And it stays there for all eternity. This is an example of fixed point behavior. Again, this is the nomenclature of dynamic systems. This is fixed point behavior. Here's another type of dynamic system. We have a pendulum, and we start it off to the right, and we let it swing, and it swings back and forth. And in a case where there's no friction, in an idealized case, this pendulum is just going to swing back and forth for all eternity, and this we call periodic behavior. Okay, so we have two different types of behavior, fixed point and periodic behavior. Both of these types of behavior are pretty simple. They're, these examples especially that I've given are not very exciting. You can imagine though, maybe especially with periodic behavior, you can have something a little bit more complex. So like the motion of the planets, for example, in the solar system, is a pretty complex system, but ultimately is very periodic and it's very predictable. And that's the key thing about these two types of systems, is that they are predictable. You can say what's going to happen 100 seconds in the future, and you'll know exactly what the state of the world is going to be. What's going to happen 2 years in the future, you'll know exactly what the state is going to be. Okay. But as I've hinted or said explicitly, there's a third type of dynamic system, which is a chaotic system. And as I've said, chaotic systems are not predictable. Okay. So that's kind of the preamble. Now we're going to actually build a chaotic system. Are there any questions until this point? So it being Processing Community Day, I'm going to use P5 to do this. And please let me know if anything ever becomes, it's hard for me to see the screen, so I tried to make the font size big enough. Yeah, maybe I'll make it a little bit bigger.
Is it possible to quickly change the color of the text?
Yeah,
the blues that you see.
Yeah,
how do I make it like that? How do I do that? Where is that?
if you just switch off the dark modes in the OS.
Yeah.
Where they go? That'd be easier to see. Should I also make the font size bigger, maybe?
Yeah.
Okay. How's that? Thank you. Okay, so we're going to start off not actually drawing anything. We're actually just going to be using the console here first. And what we're going to do is we're going to model population growth of squirrels in Central Park. Really concrete, okay? Squirrels in Central Park. And what we're going to do is we're going to model this in a discrete way. So we're going to basically we're going to be creating a function that will output the number of squirrels in Central Park every summer. So this is like a discrete, there's going to be like, the first summer, second summer, third summer, etc. Okay? And we're going to start off very simply. And I'm going to be doing some coding here. I don't actually think that the specifics of the coding are super important. So if you're not a programmer, hopefully this isn't too obscure. It's kind of more about the general ideas. But we're going to be writing a function that's going to compute the squirrel population from the previous squirrel population. And we'll call this next population. And it's going to take as a parameter the previous population. So we'll have a parameter. And then we're going to return, well, we're going to start off just by imagining the simplest thing we could possibly return, which is just the previous population. So this is a really crappy model of population growth. Basically, we're saying, what was the previous population? Okay, well, the next summer's population is just going to be exactly the same. Okay, so that's the way to get started. What do squirrels do, though, that this doesn't represent? Something very important.
Make babies.
Make babies. They're famous for making lots of babies. And so we need to represent that in our model. Does anybody have any ideas for how to do that? What do you mean by that? How would I,
They grow by 2% a year.
Okay. So we could maybe multiply the previous population by some sort of growth factor. That's what you're getting at, yeah. So yeah, we could do something like this. We could say this is not 2% a year. We're doubling every year. These squirrels are making a lot of babies, which might be realistic in some circumstances. But basically what we're saying here is we're taking the previous population, multiplying it by 2, and returning that. Okay. And now let's just, this is a very simple model, but let's just go through the motions and kind of observe what this actually does. So in our setup function, let's write some code we're going to start with 2 squirrels, and then we're going to feed in that value to our function, and then we're going to save it back out to that variable. I don't know what the level of programming literacy is here. This might be like a little bit tricky to understand, but basically the idea is that we're updating our population variable. We're taking the previous population, plugging it into our function, and then saving out the new population. Okay. And then let's add some print statements. So let's print out this population, and we'll print it out after we compute the new population, and let's run that. And you can see in the console here, we start off with 2 squirrels, and then we go to 4. Okay, great. And then we can just copy and paste this a couple times, and we can see that our squirrel population doubles in size. If we want to see what our squirrel population does kind of like super long term, like over many years, say like 100 years, we can write a for loop. So we can say from 0 to 100. And I should add that link that I showed you before. We'll have a link to all the code that I write, and I'll show you that URL at the end as well. So we run this, and we get these super massive numbers. Okay. So this is kind of working, but we've missed a really important part of squirrel population growth, which is what?
Death.
Okay, great. Before we get into death, though, I want to, and I'm very excited to get into that. I want to do one more thing here, which is I want to plot this. It's kind of annoying to just see text. So we're going to actually draw a chart of the squirrel population. So I've actually just already prepared a processing sketch. Let me just make this easier to see. Somebody said 42 before. Okay, so this is a processing sketch that I've already made, but it's going to allow us to plot the squirrel population. And so let's see if this works. So I think this slider right here. I don't know how well you can see this.
You should make your growth rate not the whole thing.
Right. Let's do 1.1. Okay. Is that visible? Yeah. That's okay. So here we're seeing like exactly what we saw in text, but we've just plotted a picture of it. And then what you just said, like let's change the growth rate. That's something that we're probably going to want to be doing a lot. So we're going to add a second parameter for our growth rate. And we're going to replace 1.1 with growth rate. And because I knew that we were going to do that, I've actually already hooked up this other slider to our growth rate. And so we can now change our growth rate. Okay. And this is already kind of interesting. Like we can see for values less than 1. I don't know if you're able to read this text right here. I can make it bigger.
You should make that background red as well.
Yeah. Background is white. Stroke black. Like that. Oh, there we go. Okay. And I'm doing all this. Yeah. Let's get through this stuff. Yeah. So now I can change my growth rate, and you can see that if my growth rate is less than 1, then I get the squirrel death, which is great. And you can see, well, it's not great, but and you can see here that I'm getting that fixed point behavior, right? We're kind of like rolling down the hill to 0, okay? And if my growth rate is exactly 1, then I get this straight line, and if it's greater than 1, then I get this exponential growth. Okay. So we're already starting to use the vocabulary of dynamic systems. So, we can say that this is like a fixed point, which is kind of cool. But squirrel populations have both growth and death in them, right? So we want to include both of these things. And the way that we're going to do that is we are. Oh, and before I move on, I should say that I kind of made a jump here that I didn't explain. So we're going to start thinking about squirrel population on a scale from 0 to 1, rather than counting individual squirrels. We're going to consider it in terms of like percent of the maximum population that Central Park could possibly support. Okay, and that's just because that's the way that this equation works. You could write it in a different way, but that's how it's written here. So that when it says 0.6 right here, that's like 60% of the maximum possible squirrel population. So now things are finally gonna get interesting, I promise. We're gonna throw in another term here. We're gonna multiply all this by 1 minus the previous population. And let's think about what this means for a second. So let's move this over. So if the previous population is high, say 0.9, 1 minus 0.9 is low, is 0.1. Okay? So when previous population is high, this term goes low, and it's multiplied by everything else. So the way that I would think about this is we're kind of scaling we're scaling the result of our previous model that we had by some new factor that is kind of works against the squirrel population. The more squirrels there are, in this summer, the less squirrels there could be next summer if we're close to our maximum population. And it's a little bit hard to reason about. I won't claim to have like the best intuition about it just by looking at this equation, and that's why we want to plot this and see what happens. But does anybody have any questions about this?
Why do we just using more to minus this? Because there can be like multiplies and other kinds of calculations. Is that like scientific or just chicken?
I picked this because I know that it leads to a cool result. So I should have said that. Yeah, this is not just me deciding that this is like a good way to model it. I read about this on Wikipedia, and I know that it ends up being really cool. Yeah. Great question. There's actually, I'm kind of embarrassed about this. Maybe some of you know where I'm going with this because you might have seen the recent YouTube video that came out. The science YouTuber Veritasium just posted something like this week that covers this exact equation. And I was like, no, that's what I'm going to talk about at Processing Computation. But luckily, whoever has seen that, you're being very polite and you're sitting through this, which I appreciate. I've linked to that video in the document that I made. So yeah, you can get that URL to that video if you want. Okay, so let's see what's so magical about this equation. So we can change our starting value. Let's start at like 50%, roughly 50% squirrels. And now let's increase that growth factor and see what happens. So at the beginning, it's not super interesting. But right when I go above 1, something new happens. We still have that fixed point behavior, but we're leveling off. We're not dropping down all the way to 0 anymore. We're kind of leveling off. And as we increase the growth factor, that leveling off point increases. And now this is interesting. If we change the starting condition, that leveling off, that convergence point stays the same. And so we've created a system that kind of doesn't care what the initial conditions are. It doesn't matter how many squirrels start out. What matters is the growth factor. That's a little bit, hard to intuit just by looking at the equation. I think it's somewhat interesting. But let's continue increasing the growth factor. So something happens about right here where we get these little squigglies. Okay? Still fixed point behavior, but there's a little bit of oscillation before we converge. And now we'll continue to increase the growth factor, and then we get something definitely different. What is this? This is periodic, right? So this is a system. We've switched from a ordered regime, fixed point regime to a periodic regime. We've built a system that can switch between these two different categories of dynamic systems. And if we continue to increase it, that periodicity splits. The periodicity doubles. Yeah. So we started with a periodicity of 2, And then there's a certain threshold where now it's repeating every 4 summers rather than every 2 summers. And if we, does that make sense? Like these values, in 4 summers from now will be the same amount of squirrels that it was today. It's not summer, but yeah, this summer. And then as I increase it, it starts to get pretty crazy, and it very quickly becomes hard to manage because we start to enter the chaotic regime. And so as I increase this growth factor, you start to get to pictures like this, where is there periodicity? Is there not periodicity? It's kind of hard to tell. If there is periodicity, if this is a periodic system, then the period must be really, really long. Longer than this chart I'm drawing here, right? And maybe it does repeat, but it kind of just feels like it doesn't, especially when I look at a variety of these pictures. Now, some of them do have repeating patterns. So some growth values do have periodicity up in this chaotic regime, but most of them kind of look like this. Okay. And there's a few interesting things to say about this. So this is chaos, and it's chaos because it's unpredictable. If we're on day 0 here, or on summer 0, and I ask you 100 days in the future, 100 summers in the future, excuse me, what is the squirrel population going to be? It's kind of hard to tell. Now you can run a simulation and you can compute it, but that's the only way to get to that answer. There's no shortcut, right? You have to go through the steps of computing every summer to get to that final answer. So it kind of looks random, right? And yet it is not random. It's this simple mathematical equation right here. There's no random number generation here. It's very deterministic, and yet it's hard to predict. So this is getting back to that idea that I discussed earlier, where chaos is unpredictable even though it's deterministic. Another thing that is interesting about this here is if we go back to the periodic regime and we change the starting condition, there's like some flip-flopping that happens, but more or less it basically stays the same. So we still have that kind of, we are impervious to changes in the initial condition. But if we go into the chaotic regime, the story changes a lot, okay? Changes in the initial condition matter a whole lot in the chaotic regime. This is what's known as the butterfly effect, which is probably like the most, the thing that's in popular culture from chaos theory. If a butterfly lands on you, it could change the entire course of your life because it creates these air vortices around your ear and you hear something a different way, blah, 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 blah. This is what that's talking about, where chaotic systems have sensitivity to initial conditions. That's really easy to see here.
Can I ask a question?
Yeah.
Is this the video that was on YouTube where it turns into like a 3D Mandelbrot? It shows the Mandelbrot set?
Yes.
So is this chaotic? But it's only chaotic because of the viewport that we're viewing. But if we actually scaled out, would you see more of the repeating non-chaos?
So the video you're thinking about, yeah, which we're going to kind of get closer to that, but that's a different chart.
Oh, I see.
So I think just to answer your question very technically though, in this chaotic regime, there is no repetition.
Got it.
Yeah.
So this is
Now-
a fractal.
Yeah.
This is truly chaotic.
This is truly chaotic. Now there will be repetition in the version of the program running on my computer, because a computer can only represent, it has a finite amount of bits,
Right.
which is really interesting actually. I mean, yeah, we're kind of like peering into this computational universe, but it's really, we're only getting an approximation of it. Because, but we're going to get closer to the Mandelbrot thing.
Got it.
Yeah. Okay, any other questions at this point? Yeah.
This how you can't predict it, reminds me of like computing things like factorial, where it's like a hard problem. You just multiply a lot of things and you can't there's no easy straightforward formula that you can just plug in and do it in one step.
Exactly.
Except that for factorial there is you can there's the trick where there is this square root of 5 or something formulas I forget what it is, but so I guess there is nothing like that, right? There's no formula that you can just derive to predict it in one go. Is that the point of that?
Yeah, and I think maybe something that you're getting at is for some problems in math and physics, there's a closed form solution,
Right.
Meaning that you can there's an analytical way to solve the problem where you just do some clever thinking and you can create a formula that is a shortcut to the answer. So you can create a formula that predicts where the ball is going to be. I throw a ball in the air and I ask where is it going to be in 10 seconds, I can compute that really efficiently because there's like a closed form solution to that problem. But there's other problems in physics that there is no closed form solution, and you have to kind of iterate numerically. You have to solve these problems numerically. And this is an example of something that you just have to iterate. Like, there's no shortcut. You have to iterate every step of the simulation to find what happens on, summer 100. And that doesn't seem so bad because, we have these computers and it can compute 100 summers of squirrel population growth instantly. But you can imagine that it might become a problem as you try to predict, farther out into the future, for example. There's kind of this incomputability hidden underneath the surface here. And this is what I'm talking about, where it's like we're looking out at the stars through our telescope. We're kind of peering into something fundamental about how algorithms work or how chaos works. That I think that can give you an intuition for maybe how our universe works. Yeah.
So is this a more efficient method for doing a random number generator?
That's a really interesting question. This was actually used to generate random numbers. It was one of the first algorithms used to generate pseudo-random numbers. Yeah. Because it turns out it's kind of a hard problem to generate randomness on the computer, because computers are deterministic. And randomness is like the exact opposite of determinism. But because chaos appears random, and yet is deterministic, that's how pseudo-random number generators work. That's how they operate. And I know, well, again, according to Wikipedia, this was used as like a pseudo-random number generator. Okay, so we're going to move on to just one final picture of the same concept. And let me change all this stuff. 42.
Hilarious.
What's hilarious?
It's the answer to life.
Meaning of life.
Not 36.
It doesn't let me do 42.
Sure it is.
Is 36 hilarious?
Yeah.
Okay. And the colors are going to switch back to what they were before, but I think that'll be okay for this. Let's just see.
Oh, yeah.
That's fairly visible, right?
Right.
Okay. Okay, so what are we looking at here? So there's kind of a lot to explain here. The top chart is still the same. So we're still looking at squirrel population over time. Okay. So the x-axis for the top chart is time, but the x-axis for this bottom chart is not time. And I'm a really shitty data visualist. I'm sorry. This is not good chart design. I should have labeled things. But this bottom chart, what it's showing is what the top chart converges to. Okay? So the x-axis here are growth factor values. So remember, this is my growth factor slider right here, and that pink line right there indicates my growth factor. How visible is that?
It's good.
It's visible.
Okay. So if I'm here in this fixed point regime, then you can see that I'm converging to a single value, and there's a single point right here. This pink line is intersecting with just a single point, okay? Because that's the point that my squirrel population is converging to. If I increase my growth factor to this zone right here, you can see that now there are 2 points intersecting that pink line. And that corresponds to the 2 points that our population is oscillating between. Okay? So this basically gives us a more general map. It actually is called a map. It's called the logistic map. It gives us a way to see, kind of from a bird's eye view, these transitions between these ordered regimes and the chaotic regime. And so you can see here that when I transition from a periodicity of 2 to a periodicity of 4, you can see that there's like this bifurcation in the chart right here. And then that moment of chaos is really clear on the chart down here. Okay. And just really quickly, just to kind of speak about how I made this chart, and you can go through the code yourself later if you want and you're curious. I'm not going to actually even look at the code, but the way it works is I'm basically iterating this population function really far into the future, and then starting to plot points after some number. So like I'm iterating it like 100 steps into the future, and then starting to plot points on this bottom chart. So for example, like if I move over here, you can see that like at the beginning, there's, well, this isn't a good example. At the beginning, there's like a little bit of, it kind of starts small and then grows, for example. And I just want to ignore this transient data right here. I don't care about what happens at the very beginning. So I wait for a bit, and then I start plotting little tiny dots on this chart corresponding to the values of the population chart. Kind of a technical detail, but you might, if you're curious about how this is actually written, it's not super complicated. And so then this chaotic regime here, you know, we've already kind of talked about this, but when we see this picture, we can see that there's some interesting stuff going on here. There's like these gaps here, right, where we can kind of go back to ordered state. So if I move my pink line over there, look, we're back to a periodic regime. So there's all these like little hidden mysteries within the chaos, and this is the thing that you mentioned, where there's actually this crazy correspondence between this chart, which is called the logistic map, and the Mandelbrot set. You can actually kind of like twist this chart and kind of like jiggle it around a little bit and fit it exactly into the Mandelbrot set. The Mandelbrot set is a famous fractal. Let's just pull it up. It's like the fractal that, you know, everybody knows and loves. This chart that I'm showing you kind of fits into this area right here. This kind of corresponds to the chaotic regime, this like long tail right here. And these like points right here where this main, what is this called, like a cardioid or cardoid or something like that, where this splits off. Cardioid. Thank you. This corresponds to like those split points in the chart. So it turns out that the Mandelbrot set is actually a representation of chaos as well. It's actually very, very similar in construction to the logistic map that we just did. It's the same thing. We were kind of iterating values and asking questions about, do those values converge or do they diverge? And so if you go on to the Wikipedia page for the Mandelbrot set, you'll probably be able to understand it perfectly well now after this primer.
Does this connect to recursion?
Does it connect to recursion? Yes, absolutely. It does in kind of a few different ways. So we're talking about fractals. Fractals have self-similarity, which means that they have like similar structures at different scales. And actually, if you were to zoom in to this region right here, you would see self-similarity. So this logistic map is a fractal. Just like the Mandelbrot set is a fractal, this is also a fractal. And you can kind of see that maybe a little bit more simply in that, like, we have this recursive tree structure, right? Like we split from 1 to 2, and then from 2 to 4, etc. So there's definitely some kind of obvious fractally things and recursive things going on, but there's actually some deep self-similarity in this picture as well. I'll also say that like dynamic systems are often self-referential, and that the current state of the system determines the next state, which is like another kind of like self-reference thing. Yeah, did that answer your question? Again, I'm an amateur, so somebody here probably knows a lot more about fractals than I do. Any other questions?
Why are there those pockets of low periodicity in the bifurcation?
I have no idea.
There's a video online that explains why that happens mathematically. It's like 18 minutes, so I won't bore you. But you should definitely watch this on YouTube, because for me, I watched it, and at the end I was just like, that's it. I pushed the computer away, and it's amazing.
I'll figure that out.
Yeah, I won't try to explain that because I don't think I would get it right. And again, I've linked some of these videos on this document. Okay, so time is almost up. I just wanted to quickly, maybe in just 5 minutes, share like how I've used the vocabulary of dynamic systems and order versus chaos in my own work as an artist. So let's go back to Keynote. Oh, let me just show this link again. So this is where all the code I've written lives. This is also where there will be links to helpful YouTube videos by the professionals.
After B comes L, right?
Yes.
Yes.
That is an L. Yes. So go ahead and take a screenshot or whatever, write that down. And so I just wanted to show this piece. There's sound here. I don't know. Okay, here's the volume. Let's start quiet. I don't know if the sound will actually work. But we'll find out. Okay. So this is a projection mapped interactive installation where you can move these sliders and adjust this kind of shape.
Was the sound also being manipulated by the
Yeah. So the sound is also generated from that as well. Yeah. Sorry that it didn't play on the speakers. Yes. Okay. Thank you.
Is there any source code for
Some of the source code is available. Not all of it, but I will. Yeah, I'll link to that. Okay. Well, I think that's a good stopping place. Thanks so much for having me.